This video discusses greedy algorithms, in particular the Dijkstra's shortest path algorithm and its implementation in C++.
A greedy algorithm is a top-down approach to solving problems. It solves a problem by selecting the best option available at the moment, not worrying whether the current best result will lead to the overall optimal result. A greedy algorithm never reverses the earlier decision even if the choice is wrong. So, it may not give a solution or the solution may not be optimal. Consider an example that we have a set of buckets with various volumes. We use the buckets to carry water to fill a container. Suppose we have buckets with volume units 4, 10, 50, and 60, and the container, 204. Utilizing a greedy algorithm, we make the most greedy choice at each step. So we use the largest bucket which has a volume of 60 to carry water and fill the container. We do this 3 times. The container now has a remaining volume of 24 for filling. So, we next choose the bucket with volume 10 to carry water, which is the biggest bucket that won't overfill the container. We do this 2 times and fill the remaining volume using the bucket with volume 4. As you can see, if the container has volume 203, then it would not be fully filled using this algorithm. In general, the algorithm is simple, but it may not find a solution and the solution may not be optimal. Here's another simple example. We want to pay $2.30 using coins, quarters, dimes, and nickels. Using the algorithm, we pay 8 quarters and 3 dimes. The following is the pseudocode of a greedy algorithm. We are given a set C from which we choose elements to solve a problem. We start with an empty solution set S. While C is not empty and S is not a solution yet, we continue to do the following. We select the biggest element X from the set C and remove it from the set. If including X in S is feasible, that is, in the above example it does overfill the container, we insert X in S. When we exit the while loop, we either have found a solution, which may not be optimal, or could not find a solution using this algorithm. To elaborate on this concept more, let's consider a well-known problem. Finding the shortest paths from one location to other locations. This problem can be solved using a greedy algorithm called Dijkstra's shortest paths algorithm. In this problem, we are given a directed graph, G, V, E, consisting of a set of vertices, or nodes, V and a set of edges E. We want to find the shortest paths from a source vertex U to other vertices. For example, we can take U to be vertex 0. To solve the problem, we consider 2 sets of vertices C and S. At every moment, the set S contains vertices that have been selected. The set C equals V minus S is the set of remaining vertices, whose minimal distance from the source is not known yet. In other words, C union S equals V, the graph vertices set. Suppose the graph has n vertices, and the vertices are labeled from 0 to n minus 1. So V equals 0, 1, 2, n minus 1. L, n. N is a matrix denoting the lengths, or weights, of the edges. L, I, j equals the length of the edge, I, j, if I, j, is in the edge set E and is equal to infinity otherwise. For example, let's consider the graph shown in this figure. Here, L, 0, 3 equals 100. L3, 0 equals infinity. L is referred to as an adjacency matrix. The complete matrix is shown here. Suppose array D holds the lengths of the shortest paths. The following shows Dijkstra's shortest paths algorithm. Here, the source vertex is vertex 0. We want to find the shortest paths from vertex 0 to vertices 1, 2, 3, and 4. The algorithm proceeds as follows on the above graph. In the beginning, S consists of vertex 0 and C consists of vertices 1, 2, 3, and 4. D1 is 50, D2 is 30, D3 is 100, D4 is 10. Because D4 is the shortest, we select vertex 4 to be in S. So now S has 0, 4 and C has 1, 2, 3. For each vertex I, we compare Di with D4 plus D4I. If D4 plus D4I is smaller, it means the path to vertex I via vertex 4 is shorter. We then update Di to D4 plus D4I. We then update D for each vertex. As you can see here, the path from 0 to 3 via 4, distance is 10 plus 10 equals 20, is shorter the direct path from 0 to 3, distance 100. So, we update D3 to 20. This is the new D array and the smallest of the vertices, and C is 3. Distance 20. So we select 3 to be in S. Now the path from 0 to 1 via 3 is shorter, so we update D1 to 40, 20 plus 20.
So the next, we select 2 to be the V to be included in S, because between the D1 D2, the D2 is smaller. So that means now the synergetic set becomes 0, 4, 3, 2. And we just need to consider the path to 1 and see if there's a shortest path. And again, we see that if the path goes from 0 to 2 to 6 to 1, it is 36. It is shorter than the current 40. So that means again, it is better to go via 2. So we update this 40 to 36. And so we have one vertex remain. So we put this one in the set S. The last step is redundant. So basically, we just need to go through these steps 3 times. Besides the initialization, 1, 2, 3. For 5 vertices. And this is the algorithm of the Dijkstra's shortest path algorithm. So we are given the adjacency matrix L and N, and Dn contains distances from 0 to the other n-1 vertices. It will hold that. And to begin, C contains the set of all the vertices besides the source. So here, like here, it is 1, 2, 3, 4. And S is V minus C. So the beginning S is just vertex 0. And we net the shortest distances Di at the beginning is L0I. That means from the source to all other vertices. That's what we have at the beginning. And then we repeat this loop n-2 times. For each time, we choose some vertex in C with the minimum D. So that's what we do. So at the beginning, we choose the minimum D. So there's D4 is minimum. And then we include this in S. And we take away this from C. So take 4 to S. And what we have to do this n-2 times, as you can see that this loop. Besides the initialization, and the last step, Okay, we omit that. So there are n minus 2. N is the number of vertices. And then for each vertex in the set C, we have to consider their corresponding D's, the distances. And find if we could find a shorter route. So if we find that, the path via the vertex V, the newly included one, is shorter than the current D, then we update it. Otherwise, we just keep the original one. So here at the end, after these n-2 iterations, we find the shortest lengths for all the vertices. And the path, or a corresponding path, can be obtained by tracing the vertices it has passed. And now you can see that each vertex will be scanned. V times V is the number of vertices there. And each edge requires constant time to update D. That's constant time. So that means the time complexity is in theta now V squared plus E. And this is basically V squared. V is the number of vertices in the graph. We just mentioned that a greedy algorithm may not find a solution or may not give the optimal solution, but in this case, the Dijkstra's algorithm, it finds the shortest path from a source, a single source, to the other vertices of the graph. So that means the solutions are optimal. And you could prove this by mathematical induction. First, for the base case, at the end of the first iteration, S has 2 vertices. So you can say that S is equal to 0 and V1. And from 9, this line, we choose the minimum D. From this line, dV1 is minimum. So that means the theorem is 2, the shortest. If we only have 2 vertices. And now we assume that the theorem holds at the end of the kth iteration, or you can say that it is at the beginning of the k plus 1 iteration. So in this case, S will have say k plus 1 vertices. We call that 0, V1, V2, blah, blah, Vk. And the corresponding distances dV1, dV2, blah, blah, up to dVk. Now, we consider the end of the k plus 1 iteration, or the end of the next iteration. Now, 9, 10 here. Always adds a new vertex. And suppose we call this vertex V dash. And we add this to the set S. And it has the smallest D value among all the unselected vertices. So that's what we do. We take the minimum dV. So we claim that this is the appropriate choice in the sense that the cheapest way to get from 0 to V dash is through selective vertices in S. If this were not true, then there's a powerful V vertex X which is shorter. Then we would not have selected V dash. We would select the other vertex. Okay. So after we have chosen V dash, dV dash is cheapest between 0 and V dash for the synaptic vertices. Okay. And 913 ensures that this is true for the rest of the unsynaptic vertices after including V dash in the set. Okay. So we always choose the minimum D values. Okay, we update the D values to ensure it is minimum. Okay, in 913. Okay. So that's the proof. Okay, and that's the Dijkstra's shortest path algorithm. Okay, and now we can implement this algorithm using the C++. Okay, so we need to have 3 sets. Okay, so to do that, let's do this. So this is the program. Okay. To do that, we have to include these headers. Okay, because we'll use sets. So we include the set header and also the algorithm to find the difference between 2 sets. Okay. Now this is a function print set is straightforward. We use an iterator to iterate through the set and just output the values, okay, of the element that the iterator is pointing at. Okay. And we implement the function vertex in C with minimum D. That is this function. Okay, with minimum D, we implement this one. Okay, in this way. So again, we use an iterator. We start with a minimum variable with values very large, and V is a vertex. Okay, and we use the iterator to iterate through the set. Okay, the set C that contains all the vertices that's not selected. Okay, and D will be the length. Okay, the shortest length contained so far. Okay, so we iterate through that C, and then compare the value. Not compare. Sorry, I mean to find the vertex. Okay, at that iterator. Okay, and then if the value is smaller than the minimum so far, then we update it. Okay, so that's very straightforward. And at the end, we return the vertex that has the minimum D. Okay, so that's the implementation of the vertex in C with minimum D. Okay. And now, so we use the example that we discussed. We have 5 vertices. Okay, so NV equals 5. It is the number of vertices, NV. And we label the vertices from 0 to 4. Okay, 0 to n minus 1. So there's 0, 1, 2, 3, 4. Okay, and then the set V, okay, is the vertex set. So using this constructor, we'll have V equals 0, 1, 2, 3, 4. Okay, this set. And then C, we construct it in this way, A plus 1, so it points to 1, okay, to the end of the array that points beyond it. Okay, so that's A plus 5. So that means C will contain 1, 2, 3, 4. Okay, and S is empty. Okay, and then we use an array, we call it vertex S, NV, this array. Okay, the 5 here, that will hold the path for each vertex. Okay, so DNV, this array is the shortest distance away, L, NV, NV. So this is the adjacency matrix that we have been discussing, this one. So this to be given. Okay. And to begin with, we set all values to infinity. Okay. So here we have L00 equals 0, L11 equals 0, but here we make it to be infinity. So it doesn't matter because we really do not use the values Lii, like L00, L11. Okay, so it doesn't matter whether we set them to 0 or infinity. Okay, and then we assign the values. 01 is 50, 02 is 30, 03 is 110, okay, and 21 is 6, okay, and so on. Okay, others are infinity. Okay. So at the beginning, okay, di will be L0i, 0 to the vertex I. Okay, vertex 0 to vertex I. Okay, and the vertex S that will hold the path, okay, is assigned I. That means directly from 0 to I. Okay, at the beginning. Okay, and for vertex S0, it is 0, the source vertex. Okay, and again we define an iterator of a set. Okay, IT. Okay, so at the beginning we print this out. Okay, what do we have in set V? Okay, set C, set S. Okay, V is the vertex set. Okay, C contains the remaining vertices, and S is the set of selected vertices so far. At the beginning, it is the source. Okay. And then we do this loop for n minus 2 times, and it's the number of vertices, okay, or MV here. Okay. So as we said, we have to go for this loop, okay, n minus 2 times, okay. So like 5, we have to go through that 3 times, okay. It is for this loop, okay. Implementation of this loop. Okay. And so this is the loop, and then we choose the minimum, the V, okay, using this function, okay, from the set C, okay, given the distances D, okay, the array, okay, array of shortest distances, okay, and then we insert this V to S. V is the selected vertex, or basically it is the union, okay, S union V. Here we implement using insert. We insert V into S, okay, and we declare variable result, which is a set of integers and a vertex, okay. So we insert V into this vertex because we only have a single element in this set, a vertex. And then now this function, okay, set difference, is to find the difference between two sets. So basically, so result here is equal to C minus V, okay, the set of V. So syntax like this, okay. So we have to have C begin, Cn, okay, a vertex begin, a vertex end, and then inserter, okay. So this is the inserter function, okay, result, result.n. So the result will be in this set variable result. So result equals C minus V. Okay. And then we put this result in C. Okay. This is our new set C. Okay. And again, we have to iterate through this C and pick a vertex. Okay. And then if the current dw, the distance, is larger than this, that means while this is smaller, while this path is smaller, then we update this dw, update this dw, and here we also record the vertex that we have used, dw, so that we can trace the path. So that's the algorithm, and so as an example, we print out the vertices V, C, S at n, and we print out the shortest distances, along with the path. So for each vertex, we start with source vertex 0, and then this array holds all the vertices. So if it is not the destination vertex, then we continue to trace forward. And at the end is the destination. This is the printing format. So we print out, after we print out the vertices, we print out the corresponding shortest distance. So now we can compile this. So it compiles and it will execute that. So that's the result, and that's what we expect at the beginning. We have vertex set 0, 1, 2, 3, 4, and C 1, 2, 3, 4, and the source, the synaptic one is the source, the 0, and then at the end we have vertex set, of course, no change. C is 1, S is 0, 2, 3, 4. So there's this step here. So that's what we have at the end. And distances are the shortest distances are 36, 30, 20, 10. That's what we got here also. But you do that by hand. So this is the shortest path algorithm with C++ implementation. Now let me show this once more. By the way, this header algorithm is for the implementation of the set difference here. Set difference. So this is the complete implementation of the algorithm, and you can always try with other graphs, whether it is directed or undirected. It works in the same way. If it is undirected, then the L02 will be equal to L20, but it still works in the same way. So this is the code. Pretty straightforward and simple. So you can try that yourself. So that's what we want to discuss today. Thank you for watching.